Imagine falling toward one of the darkest objects in the universe. Behind you are stars, galaxies, and everything you've ever known. Ahead of you is complete darkness. You continue falling, but something strange begins happening. Light starts bending around you. Time itself begins behaving differently, and somewhere ahead lies a boundary that, once crossed, will never allow you to return. This is the event horizon, the point of no return. Cross it, and not even light can escape. But what actually happens after you enter? That's where one of the greatest mysteries in modern physics begins. First, we need to understand something surprising. A black hole isn't simply a giant hole sucking everything around it into darkness. If our sun were magically replaced by a black hole with exactly the same mass, Earth wouldn't immediately get sucked inside. It would continue orbiting because the gravitational pull at Earth's distance would remain essentially the same. The danger begins when you get extremely close. Imagine approaching a stellar mass black hole feet first. Your feet are closer to the black hole than your head. That difference may not sound important, but near a black hole, gravity changes dramatically over short distances. Your feet would experience a much stronger gravitational pull than your head. You would begin stretching more and more until your body was pulled into an incredibly long, thin shape. Scientists have a surprisingly funny name for this horrifying process: spaghettification. But there's another possibility. If you approached a supermassive black hole containing millions or billions of times the mass of our sun, the tidal forces at its much larger event horizon could be weaker. You might actually cross the event horizon before being torn apart, and that's where things become truly strange. Imagine your friend is watching you from a spacecraft, safely far away. From your perspective, you continue falling normally. But from your friend's perspective, you appear to move slower and slower. As you approach the event horizon, your light becomes increasingly red-shifted and faint. To the distant observer, you never seem to cross in the ordinary way. Gravity has distorted time itself, but for you, something completely different happens. You cross the event horizon. There is no giant wall, no physical surface, no flashing sign saying you've entered a black hole. Locally, especially at the horizon of a sufficiently large black hole, you might not notice anything special at that exact instant. But your future has now changed forever. Every possible path forward leads deeper inside. You cannot turn around. You cannot send a message back outside. Even a beam of light pointed outward cannot escape. So what's waiting at the center? According to classical general relativity, a singularity, a region where our equations predict matter is compressed to extraordinary density and space-time curvature becomes extreme. But here's the important part. Scientists don't actually know whether the singularity described by classical relativity represents the final physical reality. At these extreme conditions, our current theories become incomplete. General relativity explains gravity incredibly well. Quantum mechanics explains the microscopic universe incredibly well. But inside a black hole, we need both. And physicists still don't have a complete theory of quantum gravity that successfully combines them. That's why asking what's truly inside a black hole isn't a question science has completely answered. There are ideas, mathematical models, and competing theories. But nobody can simply look inside and report back. Once information crosses the event horizon, it cannot send an ordinary signal back to the outside universe. And that creates another famous mystery. What happens to information carried by everything that falls into a black hole? Quantum physics suggests information should not simply disappear. Yet, classical black holes seem to hide it permanently. This tension helped create what physicists call the black hole information paradox. Scientists have spent decades trying to understand it, and black holes may ultimately force us to rethink some of our deepest ideas about space, time, gravity, and information. So what really happens inside a black hole? We know what physics predicts as you approach one. We can model the bending of light. We can calculate gravitational time dilation. We can simulate tidal forces. We've even captured images of black hole shadows created by glowing material surrounding them. But beyond the event horizon, Nature keeps its secret. Maybe future physics will reveal exactly what happens there. Maybe the answer will completely change our understanding of the universe. Until then, a black hole remains something extraordinary, not simply a monster that devours stars, but a place where our best understanding of reality reaches its limits. And perhaps the most terrifying thing inside a black hole isn't what we know is there. It's what we still don't understand.